Hello everyone, my name is Roger. I'm a master's student in Industrial and Agricultural Technology at Iowa State University. Today, I'll be talking about the distribution of wireless sensors due to gravity filling and the application of the sensors to monitor store grain quality. And the first objective here is to determine the distribution of two shapes of wireless sensors as a function of gravity filling a grain storage bin. And the second objective is actually the importance of placement and number of sensors on aeration control strategies and on store grain management decisions. In the first objective, we identified three main variables: the shape of the sensors, we use square and spherical shapes; the grain flow, we use 1000 and 1500 bushel per hour; and the dropout height, we used 17.5 and 13 feet. This experiment was split into three main steps. In the first step, as we see here, we put some grain, especially maize, into a bin. We measure the dropout height, and then we start putting some more grain into a bin by placing the sensors within the grain stream so that the sensors can travel through the auger with the grain. We place the sensors right here. In the second step, as someone was placing the sensors into the grain stream, another person was standing by the window of the bin and watching how the grain and the sensors will land at the grain mass surface, and more importantly, how they will behave. For instance, we see right here a sensors that fall at the grain mass surface, and we see another one that fall but is rolling away from the grain pile peak. Once we notice that all the sensors that we place landed at the grain mass surface, we turn off the overhead fill auger. Then, on the third step, someone enter into the bin and then measure the distance from the grain pile peak to the location where the sensors came to rest. Now, let's look at the result. The first table up here shows the result for the square shape sensors, and the bottom one shows the result for the spherical shape sensors. By looking at these two tables, at the beginning, it might be intimidating because there are many numbers. But if you broke this table apart, you will notice that you can actually extract three main information. First of all, we see that both sensor shapes have a wider distribution at 1000 bushel per hour compared to at 1500 bushel per hour. And that is because in the case of the 1500 bushel per hour, once the sensors fall at the surface of the grain mass, they don't have enough time to roll away or slide away from the grain pile peak, and they get buried by the grain is coming. However, in the case of the 1000 bushel per hour, once the sensors fall at the grain mass surface, they have enough time to roll away or slide away from the grain pile peak because grain is not coming faster. So that is because both sensor shapes have a wider distribution at 1000 bushel per hour compared to at 1500 bushel per hour. Now, the second observation is that the distribution of the spherical shape sensors is actually 3.3 times wider compared to the distribution of the square shape sensors. And as you saw in the videos, the spherical shape sensors actually roll away from the grain pile peak. However, the square shape sensors just slide away slowly. So as a result of that, the spherical shape sensors ended up having a wider distribution compared to the square shape sensors. Last but not least, when you look at the standard deviation of the square shape sensors compared to the standard deviation of the spherical shape sensors, we actually see that the distribution of the square shape sensors is more spread out compared to the distribution of the spherical shape sensors. And that is actually what we need. We would like the sensors to be spread out within the grain mass, basically to be located everywhere within the grain mass so that we can use them to monitor the overall grain mass in a more representative manner. So we conclude in this objective that the spherical shape sensors in this experiment roll 3.3 times further along the slope of the grain surface than the square shape sensors, and having a higher gravity feeding rate caused both sensor shapes to come to rest closer to the center peak than at a lower grain flow rate. And last but not least, the rolling distance along the slope grain surface of spherical shape sensors may be varied based on the diameter and the weight. Now, second objective here, regarding the importance of placement and number of sensors on aeration control strategy and on store grain management decision, we use a 3D ecosystem model. The model uses different principles such as mass, momentum, energy, and species balance. As inputs in the model, we use weather parameters such as wind speed, temperature, relative humidity, etc. Bin structural parameters, how small your bin is, how big it is, the height, diameter, and so on. Geographical location. We also use the internal heat, moisture, and gas generation by insect and mold. Once we have all these things in the model will then predict the grain temperature, moisture content, and gas concentration. So in our simulation, we use 3 bin sizes. We use 15 node and 30 node. In terms of sensor location, some of these nodes were placed in the center and in the 2/3 distance from the center of the bin to the bin hole. Simulation period, we start from October 1st, 2013 to September 30, 2014. Weather condition, we use EMS Iowa weather condition. Grain type, we use maize. Airflow rate, we use 0.1 CFM per bushel. And the aeration strategy here is that the fan was continuously on from October 1st to December 31st, 2013. And it was off from January 1st to September 30th, 2014. Now, let's look at the result. So these are the results for the 36 by 36 feet bin size. So at the bottom here, you see 15 node, 30 node, and total node, and the weather temperature. So 15 node, the node represents the sensors. So that basically is 15 sensors, 30 sensors. And total node here, in the case of the total node, we had 2,000 node, which means 2,000 sensors within the simulation. Now we split the result with cool down period and storage period. Now, by looking at the graph, we see that the average grain temperature given by the 15 node and the average grain temperature given by the 30 node compare to the average grain temperature given by the total node are not quite different during the cool down period, as you can see here. And we calculate the average grain temperature. We see the average grain temperature of the total node is 4.2 degrees Celsius and 4.3 degrees Celsius for 15 node and 4.8 degrees Celsius for 30 node. So we see that there is no significant difference in average grain temperature given by 15 node and 30 node compared to the total average grain temperature during the cool down period. Now let's look at what will happen during the storage period. During the storage period, the average grain temperature given by the total node within the simulation is minus 0.8 degrees Celsius and minus 4.7 degrees Celsius for 15 node and minus 6.7 degrees Celsius for 30 node. So we clearly see that during the storage period, there's difference between the average grain temperature given by 15 node and 30 node compared to the average grain temperature given by the total node within the simulation. So based on this result, we can say that the number of sensors required to keep track of aeration cooling is definitely less compared to the number of sensors required to keep track of grain during storage. So automatically, fewer sensors are required to keep track of aeration cooling compared to the number of sensors required to keep track of grain temperature during storage. This is the first observation. Second observation, when you look at the average grain temperature given by the total node within the simulation, we see that that average grain temperature is getting warmer during the spring compared to the average grain temperature given by 15 node and 30 node. So why that happened? Let's think about the placement of these sensors within the grain mass. I mentioned that in the case of the 15 sensors and 30 sensors, these are located in the center of the grain bin and in the 2/3 distance from the center to the bin hole. However, in the case of the total node within the simulation, the sensors are located everywhere within the grain mass, including in the periphery. First, now think about the grain temperature and the storegrain ecosystem in the spring, especially here, starting in March 1st. The grain temperature in the spring getting warmer. As a result of that, the solar radiation will hit the bin hole, and the grain temperature located in the periphery will getting warmer. Now, since in the case of the total node, these nodes are located everywhere in the grain mass, included in the periphery, the sensors best capture the warm temperature in the periphery. And that is why you notice that in the case of the total node, the average grain temperature in the spring starting to warm up, which is not the case in the case of the 15 node and in the case of the 30 node, because these nodes are not located in the periphery. Based on this, we can conclude that yes, the placement of the sensors within the grain mass does matter. Because if these 15 or 30 nodes were placed in the periphery, they will definitely have a warmer temperature compared to what they have right now. So now this is the result for the 36 by 36 feet bin. Now let's look at the result for the other bin, the 48 by 48 and 48 by 60, to see what will happen. 48 by 48 feet bin, so we have the same trend. Here, during the cool down period, there's not significant difference, but during the storage, we do see something. For the 48 by 60 feet bin, we also see the same trend. During the cool down period here, we have about the same temperature, but during the storage, we do see some differences. Based on this observation, we conclude by saying that fewer sensors are required to track aeration cooling compared to storage period, first. Second conclusion here is that the number and the placement of sensors does matter during the storage. And that we saw that across all bin sizes, that the average grain temperature of the total sensors is consistently warmer than those reported by the 15 and 30 sensors for the storage period. And that is due to the periphery layer effect, as I explained before. Last but not least is that as bin size increases, the surface to volume ratio decreases, and the average grain temperature remains relatively lower during the storage period. And you see here, we calculate the average grain temperature during storage period for all these three bin sizes, and you see that in the bigger bin sizes, the average grain temperature remains lower compared to in the smaller bin sizes. And the surface to volume ratio here is smaller compared to in the smaller bin sizes. So this is the conclusion that we have for the second objective. The author would like to thank the NC213 and the Amber Agriculture Company for the financial support on this project. And the author would like also to thank the staff of the ISU Agriculture Engineering and Agronomy Research Farm for the guidance and assistance in this project. Thank you.